Okay, so in this lesson, we're going to talk about matrices and systems of equations. So let's think of a matrix as a set of numbers that look like this one, and I'm going to make up some numbers. Okay, so the items that are inside, or the numbers that are inside these matrices, are called elements or entries. Specifically, we order or write the dimensions of the matrix depending on how many rows we have. So here I have 2 rows, and how many columns we have. So I have 3 columns. So this is a 2 by 3 matrix. So the order or the dimension of the matrix is a 2 by 3. So one more time, it's rows times the columns. Okay, each element or each entry that's inside the matrix, typically you'll see a variable with A, and then you'll see 2 subscripts of numbers. So let's say you see the number 1, 1. What this is referring to is the row and then the column. So element or entry, row 1, column 1, is the number 1 in this matrix because it's referring to this item or this entry or this element. Depending on the textbook, you'll see that interchanged. So if we look at this slide here, it depicts what I was mentioning before. We can clearly see this matrix, the number of rows, and then it refers to row M, meaning depending on how many rows you're given. And the number of columns referring to N. So when we're looking at M times N or M by N, we're talking about this rectangular array of entries or elements. And something that's really important to know, if the number of rows and columns are equivalent, then we call that a square matrix. So for instance, if I have, I'm just going to make up a matrix here of numbers just so you can see that there are 3 rows and 3 columns. Because the rows and column dimensions are the same, this is a square matrix. So if I had a 2 by 2, a 3 by 3, or a 4 by 4, that would also be a square matrix. Something else that's really important, if we have this main diagonal, this is referring to the entries element from row 1, column 1, row 2, column 2, row 3, column 3, etc. If I had a 4th row and column element that's in row 4, column 4, everything that falls in that diagonal here would be considered the main diagonal of the matrix. Now just take a moment and determine the dimensions or the order of each of these matrices and compare your answers to mine. So pause the video. Alright, so your answers should match the following. The first matrix only has 1 element or 1 entry in it, so therefore there's 1 row, 1 column, so it's a 1 by 1 matrix. Second one, I have 1 row and 1, 2, 3, 4 columns, so it's a 1 by 4 matrix. And here I have a 2 by 2 matrix. Here I have a 3 by 2 matrix. These two are square matrices. An augmented matrix is a way in which we can organize a system of equations. So for instance, I could take the system that I have here and write a matrix that depicts a column for X, Y, Z, and an answer column. Okay? Typically you'll see it look like this. So 1, -1, 2, so that's my X column. -4, 3, 0, that's my Y column. Notice that I'm only taking the coefficients. Next I have -3, -1, -4, that's my Z column. And now I can have my constant column, which is 5, -3, 6. So now I have an augmented matrix. It's optional to put these dots in. It helps separate your variables from your constant, or what the equation would equal. You can also have a coefficient matrix, and that would look something like this. It would be coefficients only. So notice that here I have a main diagonal, I have a main diagonal here too, and it's the same. This is an augmented matrix because here we have what our constants are. This is only a coefficient matrix because it's just the coefficients, the values that are in front of the variables. Important note, if a variable is missing and you are to write an augmented matrix, make sure that you do use 0 for any missing coefficients. Let's talk about elementary row operations. So when we talk about elementary row operations, it is elementary mathematics, multiplying by negative, adding two rows together, dividing by a value, interchanging rows, for instance. And that's what this slide says: interchange two equations, multiply by non-zero, add one row to another. For instance, here the problem says to interchange the first and second rows of the original matrix. So I want to swap these two, and that's exactly what our answer is going to show. Row 2 was swapped for row 1, and it shows you where new row 2 is and new row 1 is, right? So this row went to 2, and this row went to 1. Here it says multiply the first row of the original matrix by a half. So notice that we're writing this operation here. That's really important. So whomever is grading your paper, me, knows that you divided row 1 in half. So this must be written next to the row, so that way the reader knows that you divided in half. So 2 divided by half is 1, negative 4 divided by half is negative 2, 6 divided by half is 3, negative 2 divided in half is negative 1. Here we want to add negative 2 times the first row of the original matrix to the third row. So that was a mouthful, right? We want negative 2 times row 1 plus row 3. That gives us new row 3. So whenever you write your row operation, notice that it should be written next to the one that's being changed. So that's the last entry that should happen right here. So this tells me the change occurs to row 3. Okay? So you wouldn't write row 3 plus and then parentheses negative 2 times row 1. Don't do that. It needs to be in this order because this tells you where the entry goes. It goes to row 3. So here we had a few operations. We did negative 2 times this row. Then we added that to this row, and we got the following. And the reason why we're going to practice elementary row operations is so that we can actually use Gaussian elimination with back substitution. We already talked about that. We did this, but we only did it for system of equations using this method. However, we didn't put it in matrix form. So we're actually going to do the same thing we did in that particular lesson, but this time we're going to drop the variables and write a matrix for it. So for instance, if I had a system that looked like this. Okay, so let's take this system of equations and write a matrix for it. Okay, so I went ahead and I wrote my augmented matrix. So with the Gaussian elimination with back substitution, the goal is to get the main diagonal to be 1. Just 1. So I want this a 1 and I want this a 1. And we want a 0 in this place. So that way I can start back substituting. So we're going to work this 2-variable system first, then we'll do a 3-variable system next. And that would look like this. Okay. There's a few ways that we can get a 1 in this place, but there's already a 1 here, and maybe interchanging them seems like a good idea. So what I want to do is take row 2, move it to row 1, and put row 1 in place of row 2. So what I did was I interchanged them, and I would go ahead and I would label them just like this. Okay. The next thing I want to do is to get a 1 where that negative 1 is. So what I could do is multiply row 1 by a negative 1, and that will eliminate that negative 1 and give me the one that I want. So that's exactly what I'm going to do. I'm going to take row 1 and I'm going to multiply it by a negative, and that gives me the following: 1, negative 3, negative 12. I haven't created a change to this row. And now I have a 1 here in the first entry where I want it. And that's the first step in Gaussian elimination. The next thing I want is a 0 where this 4 is. I want a 0 where this 4 is. So what's a method that I can manipulate, or what row can I manipulate to introduce a 0 to that entry? Okay, yes, that's correct. So what we're going to do is we're going to multiply this first row by negative 4, because when we do that, I'm going to get a negative 4 here, a positive 4 here, and if I add them together, I get 0. And that's what we want. That's the next step we're going to do. So we're going to do negative, not 2, we're going to do negative 4. Negative 4 times row 1 plus row 2. And if it helps you, do the operation to the side and then substitute it. Remember, this tells me that this is replacing row 2, right? So negative 4 times 1 is negative 4, positive 12, and positive 48. And we're adding that to row 2, and we're going to get 0. 12 minus 3 is 9. 48 minus 5 is 43. And this is what it would look like when we interchange what we worked out here on the side, the 0, 9, 43, into row 2. The next thing we want is a 1 in this position. So I want you to think about, how could I introduce a 1 here? What could I do to the entire row? Good. I'm going to divide this entire row by 9. All right, and we get the following. We're going to get 1 and 43 over 9, and 0 divided by 9 is clearly 0. So now that we did that, we go ahead and in order to utilize this method, all we have to do is back substitution. Here, remember, this is column X, this is column Y. So this tells me that Y equals 43 over 9. So what I could do is back substitute into this top one, because that's what would be easier to substitute into. I have X, right? X minus 3y equals negative 12. So I could do negative 3 times 43 over 9. And we get, and I'm going to get 43 over 3. I'm going to add that to 12, and I'm going to get, so this is what we have. I went ahead and wrote it out. This gives us 43 over 3. So x equals negative 12 plus 43 over 3 gives us, oh, okay, it's 7/3. So the solution to the system, x is 7/3 and y is 43 over 9. And make sure that you go back to the originals and it works out. All right, so here we're going to solve a 3-variable system. We're going to use the same method. If you ever see Gaussian elimination or row echelon form, so I have another video that's called row echelon form and reduced row echelon form. You can use that one too to study. That's what it's referring to. So Gaussian elimination or row echelon form, it means the same thing. So I want to go ahead and start by writing my matrix. So 1, remember I have an x column, a y column, z, and a constant column. 1, 10, negative 2, 2, 5, negative 3, 4, 0, 2, 1, 0, 6. I already have a 1 here, so I'm good to go. Good to go with row 1, column 1. The next thing I want is a 0 here in this first element in row 2. So I'm going to multiply row 1 by negative 5, add it to row 2. And if it helps you, just work out on the side whatever it is that you're working on. So that's going to be negative 5, negative 50, positive 20, negative 20. I wrote 20, but I meant 10. And I'm going to go ahead and I'm going to add that to the second row. And when I add them together, here I get 0, negative 53, 14, and negative 10. So this is what I have so far. So we went, again, let's recap. We took row 1, multiplied it by negative 5, added it to row 2. I worked that out on the side, and it gave me the following solutions. The next thing I want, I can either make this a 0 or I can make this a 1. It's up to you, whatever you want to do next. I'm going to make this a 1. So I'm going to divide that entire row by negative 53. Okay, so when we do that, we took 1 over 53, or divide by a negative 53, and I got the following solution. So that gives me a 1 here. The next thing I want is a 0 here. So what I could do is multiply row 1, God bless you, by negative 2, add that to row 3. That's going to give me the following items. negative 2, negative 20, positive 4, negative 4, and we're combining that to 2, 1, 0, 6. This reduces and we get 0, negative 19, 4, and 2. Okay. So this is my matrix reordered just like that. Again, let's recap. I want a 0 here, so I multiplied this row by negative 2. So row 1 times negative 2, got this. Added it to row 3, got this. So that's my new row 3. The next thing we want is a 0 in this position. Because remember, we want our main diagonals to be 1, and we're almost there. As soon as I have a 0 here, I make a 1 here. No.
Oh, you have to make a 0 there.
I want a 0 here. If I divide negative 19 by negative 19, that's 1. That doesn't give me 0.
So add by negative 19.
If I add,
by 19.
if I add 19, the 0 is gone.
Oh.
Times the second row by 19.
Excellent. I want row 2 times 19, and then I add it to row 3. All right, so I went ahead, I multiplied row 2 by negative 19, and I got the following. 0, 19, negative 266 over 53, 190 over 53. And I'm adding it to row 3, 0, negative 19, 4, 2. Add those together, and we're going to get the following. Okay, so when we finish writing that into our matrix, it looks like the following. The next thing we want to do is get a 1 here. So we're almost there. If I multiply by a negative, I get rid of the negative. And if I multiply by the reciprocal, 53 over 54, I get 1. So that's exactly what I want to do. I want to take row 3, multiply it by the negative reciprocal. And that's going to get rid of those fractions in the bottom. So that's going to give me anything times 0 is going to be 0. 0, and then negative 53 over 54 times negative 54 over 53 is positive 1. And let's work this one out on the side. 53 over 54 times 296 over 53. So this cleans out nicely. And when we simplify 296 over 54, we're going to get negative 148 over 27. Okay. So now we have the solution for z. That's what z equals. Okay? So once I did that work, I went ahead, I rewrote my matrix. Remember, we took the negative reciprocal of row 3, and now we have what z equals. So now I can start back substituting. When I do that, I'm going to get y equals, and you can check this, put this on pause and try it, negative 34 over 27, and I'm going to get x equals 98 over 27. So on the second part of this video lesson, what we're going to do is we're going to talk about Gauss-Jordan elimination. So the Gaussian elimination is part of it, so you're going to do everything we just did, except we're going to go one step further. Not only are we going to get the main diagonals as 1, and not only are we going to get zeros below that, but we're going to want zeros above that, so that way, I'm going to just pretend this is 1, 2, 3. That way here, my answer is in the matrix. This tells me x equals 1. This tells me y equals 2. And this tells me z equals 3. So the Gauss-Jordan elimination, again, takes just an additional step of the procedures we just did and puts the matrix in the form of a solution. Okay. Another name for this is reduced row echelon form. So I do have a video on that as well.